Hello everyone and welcome. Today we're going to be discussing the wave equation in n dimensions. This is section 2.4 of Evan's book Partial Differential Equations, second edition. So just to set up the wave equation here, we're given an open subset of Rn and we're looking for a solution which is defined on this open subset capital U and its boundary. It's also time evolving, so it's a function of time here, and then the output is a real number, and we want this solution to solve the wave equation. So we ask that the second time derivative minus the Laplacian of u, and this is sometimes known as the D'Alembertian, operator, we ask that this is equal to some external forcing term f, which is specified in advance, and then some additional boundary conditions of, that U needs to satisfy on the boundary of the set U. So the first thing that we need to understand is where this equation comes from physically and what this solution means. What's the physical interpretation of a solution to the wave equation? So if we consider an elastic body, let's just consider the case of a string, okay? Then we can represent the displacement of the string, the vertical displacement of the string, by u. And so we would require a fixed point in space-time, and we can think of maybe fixing x here, so fixing a position and letting time evolve, and then this u of xt will describe the displacement of the string at that specific position x throughout time. And so the entire data of u will describe the complete motion of the vertical motion of the string in space-time. And that can be graphed as a surface over space-time, and the height of this surface is the vertical displacement of the string, okay? So now we're going to isolate a smooth subregion of U, which is we're going to call V here. And we're going to consider the mass distribution of the elastic body. So we're assuming that the total mass of this elastic body is 1, and then we're going to require that this mass distribution is constant. So it has equal mass everywhere. And this is a very simplifying assumption. Necessary to decouple mass from acceleration in this treatment of the wave equation in Evans. So when we decouple mass from acceleration, we can assume mass is essentially uniform everywhere and therefore just this constant that we can decouple from the acceleration and then use Newton's second law in the form F equals ma. So that's where we're headed. Now, if we assume this about the mass distribution, then we can understand the acceleration of the body in the subregion, and that's essentially the integral of the displacement over v, so the net displacement over v, and then and this is automatically a mass-weighted average because, again, we haven't multiplied by the mass, but the mass is just going to be the volume of the set v based on our simplifying assumptions. We take the second derivative in time, and this gives us the acceleration of the body within the subregion. Okay. Now, I will note that if we relax this assumption on the mass distribution, and we assume that the mass distribution rho is not constant, then the quantity we should be considering in our analysis is, instead of like trying to view the force as F equals ma, we want to view the force as the time derivative of momentum, okay? And so we're going to consider the quantity, the time derivative of this momentum distribution, which is the integral of the time derivative of the displacement u weighted against the mass distribution. So this will give us the momentum within this subregion. And then, and of course, this no longer requires a constant mass distribution because we're taking that into an account with this momentum integral. And then we're going to take the time derivative of the momentum in the subregion v, and this will give us the force. So in a more nuanced treatment, this would be the approach, but when we assume a uniform mass distribution, then we're good to just consider the acceleration in the region in the following manner. So since mass and displacement are decoupled here, we can bring the time derivative inside of the integral. And this leaves us with the integral over the region V of the second time derivative of u, partial derivative of u with respect to time, integrated against the Lebesgue measure here. So now, once we understand the acceleration, again, our plan is to use Newton's second law, so we need to understand the force. The net contact force on the region V is a somewhat mysterious expression, this integral over the boundary of the set V of the negative, this force vector, this force field F, dotted with the outward unit normal vector to the surface and integrated over the boundary of the surface, okay? And this F, this contact force, is the force which acts on V through its boundary. So if you picture a string that has some non-trivial displacement, then this is almost like the tension force in the spring, where you know, due to the fact that there are internal forces, elastic forces within the body, those internal forces are essentially going to add together and produce a net external force, contact force, on any given region V, which acts through its boundary, okay? And then for an elastic body, this force will be a function of the gradient, okay? Because for a higher gradient, intuitively speaking, there's going to be a larger elastic force which tries to dampen the gradient of u, okay? So we want our elastic force, or contact force F, to be a function of the gradient of u. And typically it's going to be a negative correlation, right? Because the higher the gradient of the displacement of the elastic body, the larger the elastic force will be in trying to move the body towards an equilibrium, okay? And then for a small displacement, we can use the Taylor approximation and approximate this to first order as just a constant times the gradient of u. And this approximation here, when we approximate this elastic force by some constant times the gradient of u, of course with a negative sign, then this is actually going to give us the wave equation. So let's see how that happens. Okay, so applying Newton's second law, we can set the acceleration, the net acceleration of the body in the region V equal to the net contact force of the elastic, basically the elastic force, or the net, the sum of all the internal forces of the body acting on the boundary of the set V, okay? And then we can apply the divergence theorem to identify this as the integral over the region V of the negative divergence of our force field F, okay? Before we go into some geometric interpretations, I just want to quickly mention that at this stage we have assumed away the external forces on the system. So this is the homogeneous derivation of the homogeneous wave equation, because this is just an elastic force, okay? The way that this integral was derived geometrically is due to some sort of elastic force, which is a function of the gradient of u acting on the boundary of the set. And so we get a net force essentially acting on the interior of the set, and the net force is given by the divergence of this vector field F. However, this does not account for external forcing on the system. So this is just a derivation for the homogeneous wave equation. And of course, if we wanted to derive the generalized result, we would simply add an integral to this expression, an integral over V of the external forcing, right? So again, the right-hand side of Newton's second law is just the net force on the system. So if we wanted to derive the non-homogeneous wave equation, we'd simply add a forcing term here, where we need to add the integral over V of F dx, where F is the external force and you would immediately recover the non-homogeneous wave equation. Okay? So let's now interpret this geometrically. So if let's consider 2 dimensions here. So consider a region V in 2 dimensions, and then I look at the graph of my displacement here, and I've given some sort of paraboloid, some sort of convex paraboloid. And then I look at the boundary of my set V, and at the boundary of this set V, I can see that the gradient of u is actually going to be in the outward normal direction to set V. Okay, so this total integral of the elastic force over the boundary of V, well, if I integrate this, if I just integrate this directly and I assume that F is a negatively correlated function of the gradient of u, so in particular the force F is going to point to the inside of V here, then we get a positive elastic forcing term, and so this is going to produce a net upward acceleration of the region. So the average acceleration over the entire region V here is going to be positive. And this confirms our intuition that if this is some sort of elastic body, then paraboloids of this form, which are clearly convex and kind of stretching in kind of a uniform way, downward stretching, this should accelerate upwards, right? Any elastic body, if you've seen kind of from personal experience, there's a physical intuition here that a surface or a body which is displaced in this manner should, due to elasticity, move upwards on average. Okay, and if the surface is more general than this, suppose that in some directions the curve is convex, in other directions the curve is concave, let's say, then we're ultimately looking at an average over the boundary of V, an average of this external force, and that average allows us to compute the average acceleration over the region V. Okay, so it's kind of a more global description of the motion, but if we assume this is true for all sets V, right, for any set V, then it particularly holds for sets V of a small size, and then we can kind of pass to the pointwise differential equation, the pointwise partial differential equation, which is given by basically setting these integrands equal to each other. Okay, and then if you set these integrands equal and you assume that F is just equal to, if you assume that F is equal to negative constant times the gradient of u, then you recover the wave equation. Okay, so here's another kind of geometric example here now in 1 dimension. So we're just kind of looking at another region V. This time our region V is just an interval, and we want to understand the force at the boundary of this interval based on the gradient. So we know the gradient of this function is the direction of steepest ascent. In this case, it's just the direction of ascent, so the gradient of this function, which is just going to be the derivative in this case, is going to be pointed to the left at this right boundary point. And so the force is the opposite direction, so the force will be pointed in the positive direction at this right boundary point. And then by a similar analysis here, the derivative is negative, and so the gradient is going to be pointing to the left, so therefore the force will also be pointing to the right. And so if we integrate over the boundary of V, which in this case is the 2 endpoints, and we integrate over these endpoints F dotted with the outward normal vector to V, then we're going to get a result that's approximately 0, assuming that these slopes are relatively similar. I didn't draw this perfectly, but because because the force on the boundary is the same, we're going to get a net acceleration of 0. Okay, so the net acceleration of this region is 0. You can see that maybe this region over here is going to want to accelerate upwards, but this region over here is going to want to accelerate downwards. And so our average acceleration over the region is 0. Okay, and so essentially we're deducing properties about the average acceleration of this elastic body within a region by looking at the net contact force on the boundary, and this net contact force on the boundary is a function of the gradient at that boundary. So the direction of steepest ascent of the displacement, okay? And so if that direction of steepest ascent is agrees with the direction, or at least is has a positive projection onto the outward normal vector of our surface V, then we can say that the surface has a larger relative displacement outside of V than inside of V, and that's going to cause a net upward acceleration, like in this canonical example here. This example is more obvious because it's very uniform around the boundary. All the gradients are pointed outside the boundary, so all the forces are pointing in, and that's causing a net upward acceleration. Okay, so hopefully that helps, and let me know if you have any questions on the geometric interpretation of this derivation. So to boost our geometric intuition further, let's consider a more detailed example. In this case, I'm going to fix time and consider a surface whose domain is R2, two-dimensional space, of the form y squared minus x squared. So we have principal directions. The principal direction of negative curvature is the x direction. The principal direction of positive curvature is the y direction. And the negative gradient of u, which is proportional to our contact force, is what we're assuming, is going to be the vector with components 2x and negative 2y respectively. If we choose v to be some circle in the xy plane, then we can kind of plot the direction of this vector field on the boundary of this circle. And the direction of this vector field, well, it's going to be outward facing when we get to the x direction, because of course the gradient at this in the x direction is going to be pointed towards the direction of steepest ascent. So the negative gradient will be pointed to the direction of steepest descent. So in particular, the force, the contact force at that area, is proportional to the direction of greatest descent of the surface, okay? And we can see that this vector field, this gradient of u, negative gradient of u, is actually going to rotate as we move around this circle, which is the boundary of V. This vector field will rotate. It actually won't change its magnitude, but it'll rotate until we get to the y direction. In which case, once we're on the y-axis, the direction of steepest ascent is pointed towards the origin. Okay, so in the negative y direction. And we can see that visually on the surface here. I've plotted essentially the surface above this domain here and the directions of steepest descent. Okay, and so when we look at this integral here, this integral over the boundary of V of the projection of this force field onto the outward unit normal vector with a minus sign. So without this minus sign, this is the net outward flux across the boundary of V of the force vector field V. With the negative sign, this is the net inward flux. So the net inward flux into the surface V across this boundary of our force field is going to produce our acceleration. So if you look at the net inward flux for this example, well, the net inward flux is going to be something close to 0. But the regions where the direction of steepest ascent are pointed outward to the boundary, this is going to contribute negatively. So this area in green here will contribute negatively to the net inward flux, whereas the direction in red here will contribute positively to the net inward flux. And so we see that this region over here in red, this region is going to be producing a positive acceleration of the interior, okay? So this region is going to produce a positive acceleration of the interior, whereas the region, let's say in green here, this region is going to contribute negatively to the acceleration because it's contributing negatively to the net inward flux across the boundary. So because this is contributing negatively, we can see that these regions of our saddle are contributing negatively to the acceleration of the interior. And this makes sense, right? Because if our region was a paraboloid with that's concave, okay, then we would expect that the net acceleration of this in this central region here, the net acceleration should be negative, right? Because the concave paraboloid will kind of pull down the center, okay? And that's exactly captured by the negative contribution of this vector field, this contact force vector field, the negative contribution to the net inward flux across the boundary. And similarly, in these regions in red here, if we just had a convex paraboloid, so if you had a convex paraboloid, then we would expect that, as we saw previously, the previous example, we would expect that the net inward flux is going to be positive, and that's going to produce a positive acceleration, which will lift the origin and kind of the region near the origin of the convex paraboloid in the positive direction, or produce a positive acceleration. So we can see now how the net inward flux of this force field is related to the acceleration of the region in a more geometric or a more physical manner, where essentially, if I view these tangent lines, if this tangent line with some orientation, the steeper the tangent line, the more force will be exerted, and then the orientation of this tangent line, which is the span of the gradient vector, its orientation is the direction of that gradient vector. If it's oriented such that the gradient vector is pointed in the outward direction, then that's going to produce a positive outward flux due to the gradient vector. So that's going to produce in tandem a net inward flux of the force field, because the force is proportional to the negative gradient. And so that should help boost our geometric understanding of this derivation of the wave equation. Okay, and so now we're going to go ahead and finish off the derivation by equating these integrams. So we're going to first assume, this is a small displacement assumption, that f is equal to some negative constant times the gradient of u, and then in doing so, we can go ahead and replace f by this expression. So we're going to get the integral over v, negative divergence of, and this negative sign will become a positive sign, alpha du x here. And then since alpha is a constant, this is just equal to the integral over v of alpha times the Laplacian of u. That's the definition of the Laplacian, is the divergence of the gradient. And so we end up with this expression, utt dx here. So we end up with this expression. And finally, since this holds for an arbitrary subregion V, then we can actually equate the integrands here. Okay, and equating the integrands will give us the wave equation, the homogeneous wave equation. As I discussed previously, we can get the non-homogeneous equation by a very similar derivation, just adding a net external force to the right-hand side here. Okay.